Hi, we'll look at the phase estimation problem. So what is the phase estimation problem? We have this unitary U and the eigenvector ket U of the unitary U. We know that the eigenvector of a unitary operator, eigenvalue of a unitary operator lies on the complex plane on the unit circle. So I can write this as e to the 2 pi I phi ket u. So this is the eigenvector eigenvalue equation for a unitary operator, and phi lies between 0 and 1, right? So the phase estimation problem is to estimate phi given the unitary u and its eigenvector ket u. Right now, phi is a real number between 0 and 1. So I can have a binary representation of phi equal to 0 point, maybe phi 1, phi 2, phi n, and there could be more digits up to maybe t digits, right? And so the idea is to estimate phi to a high accuracy, where you can choose the accuracy, let's say, to be n bits, so n bit accuracy. So initially what we are going to do is assume that phi is very simple. So case 1, simple case 1. Let's say phi can be represented by just 1 bit. Okay, so phi 1 can be either 0 or 1. So let's draw the circuit for this. The circuit is quite simple. You have a Hadamard gate, get 0, and then you have the eigenvector over here, and then there is a control U gate. And then there's a Hadamard gate over here, and then is a measurement. Right, so let's analyze this circuit at various points. This will be, let's say, psi 0, psi 1, psi 2, and psi 3. So psi 0 is just 0 tensor U. Psi 1 after the application of the Hadamard gate will be 0 plus 1 over square root of 2 tensor U, which I can write as 0 tensor U plus 1 tensor U over square root of 2. Next, the control unitary gate gets applied. So this is the control bit and this is the target bit. So control target, control target. So if the control bit is set, so psi 2 will be 0 tensor U. Since the control bit is not set, nothing will happen. And then in this case, the unitary U will get applied over here. Right. Now I can use the eigenvector eigenvalue equation. So this psi 2 will be equal to ket 0 tensor U plus e to the 2 pi I 0.51 1 tensor U over square root of 2. Right. And I can take the U out in common. Psi 2 will be equal to 0 plus e to the 2 pi I 0.51 ket 1 over square root of 2 tensor U. Okay, so now if I apply the Hadamard gate over here, then we'll see that if phi1 was equal to 0, then psi2 is equal to 0 plus 1 over square root of 2 tensor u. And if phi1 was equal to 1, then psi2 will be equal to 0 minus 1 over square root of 2 tensor u. Right? So applying the Hadamard gate will give me the answer. So psi3 will be equal to phi1 tensor u. Right? So we got the representation of phi over here in the top qubit. Okay, next simple case. So this was a simple case when phi could have been represented as just one bit. Suppose phi was represented using 2 bits. So simple case 2, let's say phi was equal to 0.5152. Then the circuit is the following. You have the Hadamard gate as before. Then you have another bit. So this will be 0, 0. And then we have get u. And then we have this control u gate over here, just like before. And then I have this control u square gate. And then we have a box over here, which I will, so there is some gate over here. And then finally, we do a measurement over here. And I claim that we'll get phi1 and phi2, the bits that we need on the top 2 qubits. Right? And this is right now unknown, but let's analyze this circuit. So we have psi0, psi1, psi2, psi3, and maybe over here psi4. Right? So the first psi0 is equal to 0 tensor u. Psi1 will be Hadamard gate applied on the top 2 qubits. So 0 plus 1 over square root of 2 tensor 0 plus 1 over square root of 2 tensor u. Now, psi1, so this is psi2, sorry, there is a control u gate being applied based on the control is on the top qubit. So just like before, what will happen with the phase will get kicked back. So psi2 will be equal to get 0 plus. So this analysis is similar to the one before. E to the 2 pi I due to the phase kickback 0.5152 get 1 over square root of 2 tensor 0 plus 1 over square root of 2 tensor u. Okay, just like the previous case, the phase gets kicked back. This is the control bit and this is the target bit, right? The phase over here gets kicked back to the control gate, getting this value. Now, what happens when I apply the control u square gate? So the u square gate, so what is u square get u? This will be u applied on u get u. This is equal to u applied to the e to the 2 pi I 0.5152 u. And then there will be, this will be e to the 2 pi I 0.5152 square u. Right? This is going to be e to the 2 pi I 2 multiplied by 0.5152 u. Right? which is going to be, so what happens when I multiply 2, I shift this decimal to the right. So this is going to be e to the 2 pi I, pi 1 point pi 2 get u, which is going to be just equal to 0 e to the 2 pi I 0.52 u, since e to the 2 pi I phi 1 is equal to 1, right? Whether phi 1 is 0 or 1, e to the 2 pi I phi 1 will be 1. So therefore, u square u will be e to the 2 pi I 0.52 u. Now, when I do the same thing over here, now the phase over here, which will be the phase of u square u, will get kicked back over here, right? So psi 3 will be equal to get 0 plus e to the 2 pi I 0.51521 over square root of 2 tensor 0 plus e to the 2 pi I 0.52 u, get 1 square root of 2, and then there is a tensor u over here. Yeah? So this will be psi 3. Now notice that this is the Fourier transform of phi 1, phi 2. So this is the FFT or the QFT of phi 1, phi 2. So all we have to do is to apply the inverse Fourier transform at the very end. So this question mark over here is QFT, the 4-dimensional QFT inverse, right? And we know that that is efficient. And after we apply, we'll get phi 1, phi 2, right? So that is the case when phi is represented by 2 bits. Now, next time we'll look at when phi has an n-bit representation, and maybe phi is a recurring decimal as well, in which case maybe we'll have to approximate phi to some n bits. So that those two cases we'll deal with next time.